So let's remind ourselves of where we left off when we were last talking about knots. What we convinced ourselves of was that we could come up with an invariant. An invariant is a property which doesn't depend on the diagram that I draw, but it actually depends on the knot that's behind that diagram. So any diagram is going to tell the same story if we're looking at it through the lens of an invariant. And we came up with an invariant called the Tri-Coloration Invariant. The Tri-Coloration Invariant said that whether or not a knot diagram can have its arcs colored by a collection of 3 colors, using at least one of them. So rather than coloring everything all the same color, if I can come up with a way of using at least 2 different colors to color the arcs on a diagram in 3 different colors, then I have a tri-coloration for that diagram. And remember that the rules for validity for a tri-coloration specify that a 3 coloring is valid if every time there is a crossing on my diagram, either all 3 of the arcs incident at that crossing are colored the same, or all 3 of the arcs incident at that crossing are colored distinctly. So at any crossing, either all 3 of the arcs have to be the same color, or all 3 of the arcs have to be different colors. And that's the case in which we call the coloration a valid tri-coloration. So when we looked at the trefoil, and this is going to be the knot that we start out with today, we found that it's always a valid tri-coloration to just color the whole knot the same color, because then at all of its crossings, all 3 of the incident arcs have the same color, and so on its face, this is a valid tri-coloration of this knot. But it's not a very interesting tri-coloration of this knot. What we're more interested in, because every knot has a trivial tri-coloration, we're more interested in whether or not there can be a non-trivial tri-coloration. So if by recoloring these arcs, see, now I have an invalid coloration because some of these crossings have 2 arcs the same, but the 3rd arc different. That's the one thing we cannot do in a valid tri-coloration. But by recoloring this just so, I can use 3 colors and come up with a coloration that is now valid again. Because now at every one of these 3 crossings, all 3 of the colors that we're using are distinct from one another. Every crossing has 3 different colors meeting at it, right? And so the trefoil knot, the knot we call in K32 right here, is a tri-colorable knot. It has a non-trivial coloration by 3 different colors. Is this notion of tri-coloration algebraic somehow? How do we turn this question about all 3 colors the same or all 3 colors different? How can I turn that into something that has a algebraic or even a numerical kind of reality to it that could let us investigate it with the tools of algebra that we're accustomed to using? The idea is we want a way of making the coloration criterion into an algebra problem. Coloration as algebra. So here's the way that we're going to do that, sort of notionally. Let's suppose that I have a crossing. I'm just going to draw a single crossing in sort of big format here on the page. So at each crossing I have this overstrand, and then I have 2 what I call sort of understrands. There's one understrand that creates these 2 under arcs. I'm going to draw it as though one of them is red and one of them is blue. So here is a crossing that is a part of a larger knot diagram, for example. If I want to make this algebraic, the first thing that I might think about doing is assigning a number to each one of these 3 arcs. If I do that, maybe I'll call this arc here 5. And then I'll call this arc over here, 19. Just going to assign some numbers to it. Then what I'd like to have is I'd like to have a way of assigning a number to this 3rd arc in a way that relates it to the values that I assigned to the other 2 arcs. Right? Can I come up with a relationship between the numbers that I'm assigning to these 3 different arcs such that that relationship also satisfies this validity criterion? Remember, validity means that all 3 are the same or all 3 are different, distinct. Or remember, another way, my favorite way of thinking about this criterion is that if any 2 are the same, then so is the 3rd. So is the 3rd. That's an equivalent criterion to the all 3 same or all 3 distinct. So what are some ways in which I could take 5 and 19 and maybe produce another number up here, which I know is guaranteed to be, because these 2 are different, I want to guarantee that this one is different as well. I could add them together, right? 5 plus 19 would give me 24. And now I know that all three of those numbers are different. But the problem with just naively adding together is, what if these two happen to have the same color? If these two had the same color, let's say it was 5 and 5. And by the way, I'm using the word color here, but I'm writing down integers. So what I'd like us to think about today is think about having the world's largest box of Crayola at your disposal that has countably infinitely many different colored crayons in it. One crayon for each integer. All the positive integers, all the negative integers. So when I say colors today, I'm going to be thinking about colors as integers, right? So we can do arithmetic with them. And if I label this as 5 and 5, then the problem is just adding them together is going to give me 10. But the problem is now two of my arcs are the same, but the third one is not the same as those. So clearly that's not, just naively adding together the numbers on those arcs is not going to be a good way to make this happen. So the magic solution is this. This is one of my favorite sort of ingenious solutions in all of this. What somebody figured out, I don't know who to attribute this to, is that one mathematical process that satisfies this criterion necessarily all the time is a process of averaging. If I average two numbers and those numbers are different, then I know their average is going to be different than each one of them, right? If there's actually a difference between the two, then the average is going to split that difference and be distinct from the two others. On the other hand, if I take two numbers that are the same and I average them, the average of a number with itself is going to be itself again, right? So averages have this nice property. And actually, it doesn't just work for the two numbers that are being averaged. It also works for a number and an average of that number with another number, right? If A and the average of A and B are distinct, then B is distinct from those two in turn, right? So any triplet of numbers, if one of them is the average of the other two, is going to satisfy this validity criterion. So the magic is average. So I call this the magic averaging process. If you ever get a chance to look through some of my videos from the last time I taught this course, I talk a lot about magic averages. So the magic average, the only thing we need to do to make the magic averaging process work in this diagram is how do we distinguish between the arc, which is the over arc on this crossing, the purple one, as I've drawn it here, versus the two that are the under arcs. And I think that the way to distinguish is to think about if I have an average, so I have three numbers, A and B, and then the average of the two, which is just the sum divided by 2, right? Then there is a symmetry between the role of A and the role of B in this relationship, right? The average of 3 and 7 is the same as the average of 7 with 3, right? So there's a symmetry. Even a symmetry in the expression A plus B over 2, if I switch the roles of A and B, I'm just switching the addends in the numerator of this fraction, which, because of the commutative property of addition, doesn't actually change the value of that quantity, right? So there's a symmetry between A and B, and that symmetry is broken. A and the average don't share that symmetry, right? If I switch A and B, I'm going to switch A over to this side of the average instead. So all of which is to say that we probably want the overstrand to be the one that we associate this average to, because the two under arcs, the red one and the blue one here, have this kind of symmetry associated with them, right? If I turn this whole diagram over to flip-flop the blue arc with the red arc, right, then I want still to have the same sort of process happening at this crossing. I get sort of the same diagram if I don't have any colors on them. And so the agreement that we make and how we assign colors, and by colors again I mean integers for right now. Later on, we will go back to finite boxes of crayons, finite sets of colors. But for right now, for today, we want to think about having an infinite number of different colors, each one carrying the name of an integer. And so the rubric is going to be that the overstrand is going to be the average of the understrands. Over is the average of the unders. And so, for example, if I started again with 5 and 19, the way that I did before, then to find the number that I would associate to this other undercrossing here, I would just have to say, well, 19 is the average of 5 with what? Right, so 5 plus what over 2 is equal to 19. And so I would just grind this out. 19 times 2, 38. Subtract 5, and I get 33. So I can use this rubric, the over is the average of the unders, to, given any two of the integers in this diagram, I can figure out the third one, right? So if I happen to know both of the unders, I can just average them to get the over. If I know the over and one of the unders, then I can use this kind of process to figure out the other one of the unders, right? And when I do this, I know for sure that no matter what, any two values, a and b, that I assign to any two of these arcs, the third arc, I guess this would be 2b minus a, or something, right? The third arc is always going to either be distinct from both of a and b, or it's going to be equal to both of a and b. And there's no other option, right? So we're always going to get a valid way of coloring this crossing by using this over is the average of the unders property. What does this have to do with rational tangles? Because so far we've thought about colorations in terms of knots and the diagrams for knots, and we haven't yet sort of connected that to where rational tangles happen. So that's where I want us to start the story today. How do we get a tangle out of a knot? And the good news is that it's a fairly straightforward process. You have to imagine having a copy of this knot on the table in front of you and just picking two places on this knot diagram where we're just going to cut. We're going to snip the knot in two different places. And that's going to open up two little ends on my knot. I'm going to see if I can sketch this out to try and convey what I'm trying to say. So the picture that we want to have in mind is just picking 2 points on this trefoil. Let's say I picked this point right here, and then maybe I'll pick this point over here. I don't know. I'm just going to pick a couple of arbitrary points. And we imagine that we're just going to cut the knot in those 2 places. And then we're going to pin the knot down like it's a butterfly getting pinned to an entomologist butterfly board, right? So we're going to pin those 2 places up there in the northwest and the northeast corners. And we'll pin these other 2 places on the southwest and the southeast corners. And now what we hope is that we have created a rational tangle in the process, right? And you may need to squish the strands around a little bit to try and uncover what rational tangle it is that we're looking at. But that's actually where I want us to start this process today. So it's actually what I'm going to ask your groups to do first, is to, starting with the diagram of the trefoil, pick a couple places to cut that diagram and see if you can figure out what rational tangle it is that corresponds to this knot. And we should be able to also go back and forth. That's the last thing I'll say before we get into our groups. Given any rational tangle, I'm going to call this Q, we can turn a rational tangle into a knot. And all we have to do is just undo what we did here. Take those open ends that we created when we cut this knot apart, and we just sew those open ends back together. All we have to do is connect northeast to northwest and southeast to southwest. And we create what's called the numerator closure. Numerator closure, N of Q. And this is going to be a knot, we hope. And it's a particular kind of knot, unsurprisingly, called a rational knot. So any knot which can be obtained as the numerator closure of a rational tangle is called a rational knot. And the fact we have to make that distinction at all suggests that maybe not every knot in the world is a rational knot, but it turns out a whole bunch of them are. And so a lot of the times we can study the properties of knots by studying the rational tangles that they're associated with. And in the process of cutting this knot apart and pinning it down so that it becomes a rational tangle, we find out that, in fact, we end up getting just a very simple rational tangle that looks like this, right? And this rational tangle consists of 3 consecutive twists of the northeast over the southwest, or the northeast over the southeast strand, excuse me. And so as you all correctly noted, right, this has the rational tangle word TTT. All right, you start with an empty tangle and just do 3 twists of northeast over southeast, and we get this tangle. So we're going to call that tangle Q. And the fraction of this rational tangle is that fraction that we would get by starting with the tangle number of an empty tangle, which is 0, and then applying 3 consecutive twists, and every twist we apply to a rational tangle increases the tangle fraction by 1. So we're just going to add 1 3 times and get a tangle fraction of 3. Right. So another way to say this, right, is that the trefoil knot, this K32 trefoil knot that we've been studying, is a rational knot because it's the numerator closure of the rational tangle whose tangle fraction is 3, and which we know in rational tangle word as t to the power 3, right? So what we want to do next is we want to go back to this idea about the magic average, right? Using integers to successfully represent this behavior of all three arcs having the same designation at a given crossing, or all three arcs necessarily having different designations at that crossing. And by agreeing that the overcrossing will be the average of the two undercrossing arcs at each of the crossings, we will achieve such a property, right? We're guaranteed that if we do that property at every single crossing in the diagram, we're going to get a valid integer coloration at the end of the day. So here's how it happens. What we're going to do is pick a corner of the rational tangle to get started. And for convention's sake today, we'll use the northwest corner as the place where we're going to start our coloration. And then out of that northwest corner, right, we have an arc. And that arc is going to encounter a crossing right down here. So the first thing that we'll do is we'll just decide on integers that will sort of seed this process. And I'll do that by assigning the number 1 to this first arc that's coming out of the northwest corner. And I'll assign the number 0, because I want to use kind of the simplest numbers possible, right, that we can get away with. And we want to make them distinct. Otherwise, if we don't make them distinct, what's going to happen is that every single arc is going to get the same number in the entire diagram, which, while it's a valid coloration, it's not a non-trivial coloration. So we want to pick two different integers to get the process started, right? And so I'll pick the two simplest integers there are, 0 and 1. And then all I have to do is at each one of these crossings, now that I know what integer is coloring two of the arcs, I'll just use that integer to figure out how to color the third one. Right? So at my first crossing here, my over arc is a 1, one of my under arcs is a 0, and the over has to be the average of the two unders, right? And so how we would do that, right, is we would say 1 is the average of 0 with blank, and then we would just work that piece out, right? So we could do that a couple different ways. 1 is equal to 0 plus x over 2. Whoops, move that down so you can actually see it. Right, and then we would just solve that equation for x. X equals 2 times 1 minus 0, otherwise known as 2. So then that gives me a color of 2, an integer color of 2 for that next arc coming out of that crossing. And that arc is going to have a color called 2 for its entire sort of life, right? So any crossing that it comes to, that arc is going to have a number of 2. But now at my second crossing here in the middle, 2 is now my over, and my under, the under that I know, is 1 from over here. So now I've got 1 as an under and 2 as an over, and so the unknown undercrossing here, undercrossing arc, is going to have a color such that when I average it with 1, I get 2. And so there the color is going to be, I guess we would call it 2 times 2 minus 1, right? If we do that same arithmetic, 2 times 2 minus 1 is 3. And so then this arc is going to have a color of 3 for the rest of its life. And now I just have one more arc to color in this diagram. It's this one right here. The over arc is 3, the under arc is 2, and so the unknown under arc is going to be twice 2 minus 3. No, sorry. It's going to be twice 3 minus 2. Twice the over minus the under. 2 times 3 minus 2. Do that out. We're going to get 4. And so at the end of the day, I've now colored, quote unquote, each one of the arcs in my tangle diagram with an integer, such that at every crossing, either all three of my integers are equal, or, as is the case here, all three of my integers are different at each crossing. Because at each crossing, the over arc is the average of the two under arcs. Right? So what can we do with this? Well, what we'll do with this is try, and this is the other amazing thing about this, try to see if we can capture enough, or ideally all, if we can, of the behavior that we're interested in. Can we capture it all just by looking at the numbers that result at these 4 corners? So let me sneak this over a little bit just so we can see it. So at the four corners, we end up with these four integers. I get a 1 in the northwest. I get a 0 in the southwest. I get a 4 in the northeast. And I get a 3 in the southeast. And so one thing we could do is say that the integer coloration of this rational tangle could be represented by a matrix. So here come the matrices again. It's supposed to be good news, but it always feels like bad news initially. So we have this matrix 1, 4, 0, 3 that we think is a way of representing this rational tangle just by encoding what are the colors that I get at each of the four corners after I do this integer coloration process. So this was the next thing I'm asking you to do in this activity, is to do this tangle coloration process to figure out what we call this, the coloration matrix for this rational tangle. But, and this is where I'm going to ask you to pick up the story, we made a couple of choices to get the process started. Right? We chose a 1 and a 0 as my first pair of distinct integers to get the process going. What if we make a different choice and then sort of chase through that coloration and figure out if we can tell whether or not the choice that we made there actually affects our answer? And if it affects it, how does it affect it? And then most interestingly for me, and I hope for you by the time this activity is over, is how does this viewpoint that we took here, creating this coloration matrix, how does what that matrix tells me relate to what this tangle number was telling me? Is there a relationship? Can we find a relationship between the coloration matrix and the fraction of this rational tangle? Because if we can, it's going to give us a really handy way of using coloration, integer coloration, to determine the fraction of a rational tangle. So, this was a really successful group brainstorming and conjecture session. I can tell it's successful because I know the end of the story, right? So I have that hindsight bias. But so you came up with a variety of different coloration matrices for the same rational tangle, which in this case was just the rational tangle t cubed, right? And each one of these matrices, the first thing that you all noticed was that there was this diagonal property, that the sum of the numbers we get on the diagonal is always the same as the sum of the numbers we get off on the anti-diagonal, right? In the original matrix, 1 plus 3 was equal to 0 plus 4. And all these other matrices, 10 plus 16, 26, which is the same as 19 plus 7. 6 and 14 are the same as 18 plus 2. So that diagonal property is super helpful because it also implies, and you showed that this was just a simple algebraic manipulation, it also implies that the difference between the rows, so the difference between the two rows of each of these matrices, is the same in the first column as it is in the second column. So in this green matrix up here, 10 minus 2 is 8, and so is 34 minus 26, right? 1 minus 2 is negative 1, and so is negative 2 minus negative 1. So the difference in the rows is the same in each column. And also, the same is true for the columns. The difference in the columns is the same in each row. So 19 minus 10 is 9, and so is 16 minus 7. Right? So that diagonal hypothesis is super powerful because it means if I care about the difference between the columns, I only have to compute one of those differences. If I care about the difference between the rows, I just have to compute one of those differences as well. Okay? And the real kicker is the conjecture that's above my head here, which is that if we take the difference in the columns, so the second column minus the first column, and we divide it by the difference in the rows, the first row minus the second row, then what we will get is, in fact, the fraction of our matrix, or of the rational tangle, which has this as the coloration matrix. And again, independently of which numbers we chose to start the integer coloration process, by the end of it, we get a matrix, and the column difference divided by the row difference for that matrix is supposed to give us the fraction for this rational tangle. So this is a really good conjecture. You notice that no matter what A's and B's that you chose for this particular tangle, which is just 3 twists, right? That if you start with A and B here, that the entries you get in the other corners are 4A minus 3B, 3A minus 2B, for which the column difference is 3A minus 3B, and the row difference is A minus B. So when I divide the former by the latter, the former is just 3 times as large as the latter. And so when I divide them, I get 3, which is, in fact, the tangle number for this rational tangle. So this is what we want to assess after we take a short break, is we have this conjecture How could we prove that this does or in fact does not always happen? So I want to take 5 minutes, come back at 20 till, and we'll come together and see if this actually is borne out in the algebra. So let's take 5. So what do we make of this claim? The claim that the fraction for a rational tangle Q, once I've given it an integer coloration that has color matrix A, B, C, D, that I can take the difference in the columns, measured, for example, by the difference B minus A, and I can take the difference in the rows, for example, as measured by the difference A minus C, and divide them to get my fraction. So how are we going to come up with a proof for this? And the proof for this has to start the way that rational tangles start. The proof is done by an induction, and that induction is done on the ways that rational tangles are created. Okay, so we start with the empty tangle. The empty tangle is my base case. When Q is my empty tangle, which, remember, is just a pair of horizontal attachment strands like this, right? Let's think about what a coloration for this empty tangle would look like. What must be true for any coloration matrix of the empty tangle? So if I come up with, no matter what numbers that I start with, let's say that I put an A over here and I put a C over here to get my coloration started. What are the other two corners going to be? The other two corners are A and C again, right? Because all I've done is connect this corner to this corner with a single unbroken arc. So these other corners are going to remain A and C, respectively. And so every color matrix that I could come up with for an empty tangle is going to look like this. So what is the fraction of an empty tangle? What is the fraction number that represents the empty rational tangle? Where did the process start? When we were using the process last week to find the fraction of a rational tangle, what number did that process start with? When you're it started with 0. When you're reading a tangle word from left to right, we start with a number of 0 because 0 represents the empty tangle. 0 is also how we know that we've untangled a tangle, because we've gotten the tangle number back to 0. Right? So for an empty tangle, we know that the fraction is equal to 0. And we can check that when I take the difference in the columns divided by the difference in the rows, so if I just take the difference between these, between A and A, this difference is 0. And I divide it by the difference in the columns. The difference in the columns here is A minus C, which by hypothesis here is not equal to 0, because we always want to start our coloration with two different integers. That what I'm going to get here is A minus A over A minus C. 0 divided by A minus C, that's equal to 0. So my base case works out, right? This recipe of dividing the column difference by the row difference does give me the right fraction for the empty tangle. So that gets our process started. We know that if my tangle starts out as empty, we know that this rule is going to give us the right fraction for an empty tangle. So now for our inductive step, there's two things that we need to check. Inductive case. We need to check that if I start with any rational tangle at all, and we assume that this formula gives us the correct tangle number, we need to make sure that the correct tangle number is still preserved after we have added a twist onto my tangle, and also that this recipe still works after I have added a rotation onto my rational tangle. So those are my two inductive cases. My first inductive case is the case in which we assume that our recipe is correct, and we want to check that it remains correct after we add a twist. So let's just check real quickly to see what happens if I take a tangle which has coloration matrix A, B, C, D, and whose fraction, so my inductive hypothesis here is that this difference B minus A over A minus C is indeed the correct way to find the fraction of this tangle. And if I just add a twist to it, so if I add a twist to it, northeast over southeast, Then the question is, what are the new labels at the northeast and the southeast corners? Let's start with the one that's simpler. What's this southeast label going to be? What's the color of this arc? Because it was the over arc at this crossing, we just trace it back over here and find out that this was the arc that had the color B, right? So B is now the color of this lower right-hand corner. Meanwhile, the upper right, so this is why it's good that you got practice doing this with the formulas, with the ABCD in it, in the algebra before we got here, right? Because it's the same process we're going to do to figure out how to color this upper right-hand corner, right? The overstrand is B, the understrand over here is D, and so this upper right is going to be twice the overstrand minus the understrand, 2B minus D. And so if I call this new tangle Q prime, I want to know whether or not my recipe, column difference divided by row difference, I want to know if that recipe still gives me the correct formula for this tangle, the correct tangle number, rather. And so I'll do the process of taking the column difference. And my column difference we can write as either 2B minus D minus A on the one hand, or I could write it as B minus C on the other hand, because those two things are equal, right, according to our diagonal hypothesis. So I'm going to call the column difference, just to make my life easier, I'm going to call it B minus, do I want to do it that way? No, I think I want to do it this way. 2B minus D minus A. There's my column difference. And then my row difference is going to be A minus C again. Right? So that is what this claim would say for this tangle after I've added a twist onto it. And so if we can simplify this somehow, then hopefully we'll be able to find out whether it bears a relationship to the original tangle number that we started with right here. Well, one nice thing that I'm noticing is that the denominators are at least the same before and after, right? So let's see if we can figure out how the numerators are related. In particular, how does this numerator relate to the numerator over here, which is B minus A? So to figure that out, I'm just going to split apart this 2B here into a B plus a B, right? So that I can get one of those B's together with this minus A over there. So we'll write this as B minus A plus B minus D divided by A minus C. Not too controversial, I hope, right? Just split two B's into separate addends. And now I have a lot of what I liked about my original. B minus A is up here, A minus C is down there, and I have this extra B minus D that I don't quite know what to do with. So I'll look over here into my box of tricks and see, is there anything I can trade out B minus D for? Well, B minus D is nothing more than the difference in the rows of my original tangle, which I can write as B minus D, but I could also write it as A minus C. And so I'm going to do that instead. I'm going to use that trade-off here to replace that B minus D with an A minus C. And check this out. I have an A minus C term up here on top. It's also equal to my denominator. So if I split apart this fraction at that plus sign that's up there on the top, I can write this as B minus A over A minus C plus A minus C over A minus C. And A minus C over A minus C is otherwise known as 1. And so the question I have is, what did we expect to happen to the tangle number of my original tangle when I add a twist to it? What happens when you add a twist to a rational tangle? What does its tangle number do? So it goes up by 1. Exactly the thing that we hoped would happen when we added a twist is that the tangle number goes up by 1. That happened when the tangle number was computed using our fancy column difference divided by row difference hypothesis, right? And so this is exactly what we want to happen when we add a twist to a rational tangle. Q prime was obtained from Q by adding a twist, and correspondingly, its tangle number is obtained from the tangle number of Q by adding 1. So that's good news as well, right? We have the base case, we have the first inductive case, which shows me that when I add a twist, the right thing happens, right? My tangle number, as computed by this coloration fraction, increases by 1. So what do you suppose inductive case number 2 is? We know that the twist works. Yeah, we have to figure out if rotation works also. So let's roll back to our inductive hypothesis. Our inductive hypothesis is that this coloration fraction actually gives me the right tangle number for my rational tangle. Right, so f of q, the fraction of this rational tangle, is b minus a over a minus c. And now I just need to see what happens when I rotate this tangle instead of adding a twist to it. So I'm just going to take my tangle, rotate it. Remember, we decided that clockwise was the orientation we wanted for our rotated tangles. And so now my q prime, I'm just going to take and rotate everything 90 degrees clockwise so that now A is up here, B is down here, and then C is over here, and D is down there. And according to our coloration fraction, the fraction of this rational tangle is equal to the difference in the columns divided by the difference in the rows, which, if we go by our original formula, this should be A minus C divided by C minus D. Okay. And this doesn't exactly look like what we have here, but it does look like the A minus C that we used to have in the denominator is now up in my numerator, which is a good sign, because what is supposed to happen to my fraction of my rational tangle when I apply a rotation to it? What operation? What are we driving towards here? Rotation is supposed to be opposite reciprocal, right? So we already are seeing kind of a reciprocal-like behavior happening. The A minus C has sort of migrated from the denominator up to the numerator. But now we have this C minus D that we can't quite account for yet. So we go looking in this box of tricks to figure out what we can relate it to. Well, C minus D is nothing more than the opposite of D minus C. That's not too controversial, I hope, distributing the minus sign. But D minus C is something that we have a substitution for from our box of tricks that came from the diagonal hypothesis, right? D minus C is the same thing as B minus A. And so when I make that substitution, A minus C over minus B minus A, and then I can just take this minus sign out of the denominator and just make it a minus out in the front. A minus C over B minus A. And now, sure enough, what I'm looking at here is the opposite reciprocal of the tangle fraction of my original tangle from over here, right? So this is legitimately -1 divided by the fraction of q. And that's all she wrote on this, right? What it means is that because every rational tangle is created by starting from an empty tangle and applying a word of t's and r's, right, successively, and because the individual maneuvers that make up rational tangles, in other words, starting with empty, adding a twist, adding a rotation, because those three maneuvers work exactly the same for this weird coloration definition of the fraction as they did for our original definition of tangle, right? Twisting adds 1, rotating does opposite reciprocal. That we have actually a faithful representation here of how the tangle number works. So what we've proven here is that this claim is, in fact, better than a claim. We can call it a theorem. So we now know that this is a new way of computing the tangle number for a rational tangle. We can start with any pair of integers that we want to, as long as they're different from one another, and color the entire diagram. Right? Once we've colored the entire diagram using that rubric of the over is the average of the two unders, then we're going to get at the outermost endpoints, we're going to get a 4-number matrix, A, B, C, D. And that those 4 numbers can be used to compute the fraction of this rational tangle in this way. It's just the column difference divided by the row difference.